Hello, everyone, and welcome to the November episode of the Science Talks webinar. My name is Katie Ackermick-Ferris, and I am a coordinator of special events for the University of Alberta's Alumni Association. I'd like to acknowledge that the University of Alberta is located on Treaty 6 territory and respect the histories, languages, and cultures of First Nations, Métis, Inuit, and all First Peoples of Canada, whose presence continues to enrich our vibrant community. Our presentation, Climate Change on Canada's Highest Peak, is about 30 minutes in length, and we will have time for a question period. We'll be collecting questions throughout the presentation, so please type your question into the Q&A box, which you'll find at the top or bottom of your screen in that toolbar. At the end of the presentation, these questions will be shared with the presenter to address, and we'll get to as many of them as possible. So feel free to enter your questions at any time during our talk today. You won't be interrupting the presentation. A video of the presenter will appear on your screen. If it happens to obscure the presentation material, you can move it around by clicking on it and dragging it to another area of your screen. It is now my pleasure to introduce Frederick West, Acting Dean of the Faculty of Science.
Well, thank you so much, Katie. And I want to thank and welcome all of you who are joining us today for this month's Science Talks webinar. It's always such a pleasure to connect with all of our friends out there in the larger world and share some of our excellent research that's happening here in the Faculty of Science. Before I introduce our speaker, I'll just highlight a couple of points for those who might be interested. We did celebrate our convocation last week for the fall graduates, fall 2022 graduates. And science actually had by far, I believe, the largest cohort. And it was wonderful to celebrate the achievements of all our graduates and welcome them into our growing alumni community. Also, as you may or may not be aware, next week marks the last day of classes in the fall term. Students are getting ready for exams, and we have winter break just around the corner, and an opportunity for all of us to recharge our batteries and get rested up for a new term in 2023. I want to let you know that we will, in the very near future, be sharing the next issue of Science Contours, our alumni magazine. And in those pages, you're going to be learning about a lot of exciting research directions and achievements of our faculty, also our alumni and our students, including a feature story on the work of the student group, Alberta SAT, which is about to launch actually their second satellite, X-Alta 2, which is going to be monitoring wildfires from orbit. And there's actually an opportunity to hear a bit more about our guest today in Science Contours as well. And I am very thrilled now to introduce our guest speaker, Alison Criscitiello. Let me say a few words about Alison before I hand the floor over to her. Alison Criscitiello is an ice core scientist and high altitude mountaineer. What a combination. Dr. Criscitiello's research explores the history of sea ice in polar regions using ice core chemistry. So she drills ice cores all over the world: Antarctica, Alaska, Greenland, the Canadian high Arctic, Yukon. She is also the director of the Canadian Ice Core Lab here at the University of Alberta and in the Faculty of Science, based in the Department of Earth and Atmospheric Sciences. She's also an adjunct assistant professor at the University of Calgary. Alison holds the first PhD in glaciology ever conferred by MIT. She is a former US climbing ranger, has guided expeditions to major peaks in the Andes, Alaska, and the Himalaya. She's been named a National Geographic Explorer and a fellow of the Explorers Club and Royal Canadian Geographical Society. And probably many of you have read about Alison's exploits in the news over the last few years. She certainly got a lot of amazing coverage that then sort of trickles down to the Faculty of Science. And she's certainly one of our real stars, research stars. She's also the co-founder the founder and co-director of Girls on Ice Canada, a tuition-free science immersion summer wilderness expedition program for high school girls. So in case it's not clear, Alison does it all. And she's also a fantastic speaker, as I'm sure you will find out momentarily. So without further ado, welcome, Alison.
Thank you so much, Fred. Give me one moment to share my screen here. Okay. Thank you so much for the introduction, and hello to everyone. It made me smile real big to see people from all over, and also to see Parks Canada here, who's a very important partner on this project. So hello to Haines Junction. Well, thank you again for the intro and for this opportunity to speak to you today about this project that's very near and dear to my heart. Now, as Fred mentioned, I'm the director of Canada's National Ice Core Lab, which is housed here at University of Alberta in the Faculty of Science. And I just wanted to first mention that this work that I'm sharing with you today has taken an enormous, incredible team to complete. And by no means is this me alone. And I wanted in particular to highlight my amazing PhD student, Kira Holland, who's really co-leading this work with me and whose research, which you'll see in the next few years out in the world, will be focused on this new Mount Logan climate record. I'd also like to recognize that none of this work that I'm sharing with you today would be possible without the approval and the collaboration of the local First Nations, whose territory that this part of Yukon St. Elias lies within, the Kluane, Champagne-Ajac, and White River First Nations. Okay, now, let me take you through a bit of a journey on Mount Logan that covers, quickly as I can, the science, the expedition itself, and also a bit of a look toward the future. Now, first, just in a single, very overviewy slide, why do we go through this terrible trouble of drilling ice cores in really uncomfortable places? Well, they allow us to investigate past climate and environmental conditions prior to the 1970s, when the satellite era began, making them truly one of our most powerful tools for studying the Earth, long-term climate, and how humans have impacted both. The chemistry of ice cores offers a seemingly endless number of tools to investigate past climate. And I'm listing here just a few ones that are priorities for the Mount Logan ice core: temperature reconstructions, wildfire and pollution reconstructions, and looking at various chemical species to learn things about ocean conditions in the past as well. Now here, just to situate us for a minute, and also to answer a question, I think, that I get asked often. So why would we go somewhere like the summit of Mount Logan to drill an ice core? And really, that question is getting at a bigger one, which is, why do we need ice cores or climate records from various places on Earth, particularly outside of the polar regions? Why is this important? Well, ice cores contain not just global climate information, but also regional and local information. So if we rely solely on polar records of long-term climate, there would be huge gaps in our knowledge of subpolar climate history, particularly in really important regions climatically and in terms of atmospheric dynamics like the North Pacific. Mount Logan, so yeah, if you think about it, outside of the poles, there aren't very many regions that are sort of cold enough and high enough over very long periods of time to preserve long climate histories, like tens of thousands of years. And Mount Logan is one of them. And among the other few, such as its sister peak over the Alaska border, Denali, still it is unique. By mass and base circumference, it's the largest non-volcanic mountain on Earth. It sits within the largest non-polar ice field on Earth. And its summit plateau, which is around 17,500 feet in the free troposphere, is enormous. It's 20 kilometers long, And the ice in the center of it, we now know, is much deeper than 400 meters, which is just spectacular for the top of a high peak. It's coastal, of course. This red arrow is kind of pointing to where it sits in the Yukon there, very close to the coast, just off the Gulf of Alaska in the North Pacific. And so a record from the North Pacific like this has the tantalizing prospect of containing climate information that's distinct from Greenland and other Arctic records. And I can tell you from looking at the very preliminary data that we just have in hand as of a few days ago, this is true. It is a very unique record. So the primary goal of this project was, of course, to drill an ice core on Mount Logan Summit Plateau after locating the ideal coring site with the potential to offer us what we hypothesized or suspected would be 20 to 30,000 years worth of climate history in the North Pacific. And it looks like we were right. This is a really interesting project, in part simply because of the difficulty and, of course, drilling an ice core at the top of a 5,900 meter tall mountain. And it requires this kind of dual background that I have in ice core science and high altitude mountaineering, partly why I just love this project so much. So in May of 2021, last year, I took a very small team up Logan to complete a radar survey and install a weather station. And then this past May, I took a larger team up the mountain to complete the drilling. And you'll see that in this little list here on the timeline, that since we returned in June, we've imaged and processed the ice, getting it ready for analysis. And Kira and I, in fact, just returned last week from completing the CFA campaign in the United States on the center, most precious stick of the ice. The CFA, this stands for continuous flow analysis. It's a method that allows us to melt ice continuously and directly in line with analytical instruments, offering the highest resolution data possible. And this is presently the only thing we cannot do in Canada, but we will be able to in the future. So Kira and I spent this past month completing the majority of the liquid chemistry analyses via this CFA method. And this includes all of the elemental data, major ion data, stable isotopes, black carbon, particle count, just to name a few. So we've got 90-something% of the data in hand now, but I was tempted to show it today, but it's not, of course, on an age scale yet. That will take months to complete, and it's quite preliminary. But it's a very exciting time to have it in hand right now. So outside of the CFA campaign, all the other analyses happen here at U of A in the Canadian Ice Core Lab. And I just wanted to say a quick thing about the lab here, that this is Canada's National Ice Core Lab. It is a true treasure. The facility is made up of 3 rooms. We have a room temperature analytical lab with instruments in it that are dedicated solely to analyzing the chemistry of snow and ice. There's a -26C core processing and imaging lab that we work in, and then a -40C archive room that at present contains about 1.5 kilometers of ice, almost entirely from the Canadian high Arctic, making it a worldwide unique archive. But of course, there's ice from all over the world in there. And we offer analytical services to institutions across the world. And since completion of this facility about 5 years ago, we've really forged our way to the front of the International Ice Core stage. This lab, our lab group, and the research program we've developed here have really put us at the forefront of ice core science. Now, I said I would tell you about the expedition itself second. So I'm going to show you a short video. It's a few minutes long, but they're very quick little clips. And this is a video selects reel from National Geographic, who came along on the expedition. And I just thought I would, it was a unique way to show you kind of a sense of what it was like to drill the Mount Logan ice core. And perhaps why when people ask if I would do it again, I say no. Not really, I would do it again, but okay, it's gonna go right into it. So we're gonna start off in this video on Mount Logan's Summit Plateau. You're looking at Prospector's Call here. that we're kind of flying over. And here's the broad summit plateau that I mentioned, with the true summit of Logan being in the background there. And here's sort of the backside. So when we work on a mountain this high, it requires climbing the peak so that we can safely work at altitude. So we fly into base camp, which is around 10,000 feet or just below on Mount Logan. I would say the weather is mostly not sunny. It is coastal, and all the things that make it great for drilling and ice core, like high accumulation rate, make it, stormy. So we make our way up the mountain. It generally takes teams who are just climbing it for fun, about 2 weeks. I've climbed it 3 times in 9 or 10 days, and we double carry. So here we are going up one of the first big ice falls up to Camp 1, and double carrying. This means that we climb every section twice so that our bodies can really slowly acclimatize and make sure that we're really doing well with the altitude before we ascend to a higher altitude. This camp is Camp 2 on King Call, one of the most beautiful spots that I've ever been in my life. And the crux of the route getting up to where we drilled this ice core is King Call Ice Fall. There's my climbing partner and I leading up through it this year. And these next few shots are of us picking our way through the maze of the ice fall, which I think the first time I climbed Logan was almost 10 years ago now. And it was an easy ski up and down. And I can tell you it is not anymore. And I think that the standard route may change in the coming years. It's a very mobile, thinning and accelerating ice fall. So it's interesting to ascend and descend these days. This is just above, once you crest above King Call Ice Fall, this is kind of the third and final camp that we made before jumping up and over to the summit plateau. I don't remember the altitude here, but around 16,000 feet. Suddenly we're on the summit plateau because the weather was that bad. There's no footage from going up and over Prospector Call. But when we arrived up there, very talented helicopter pilot, sling loaded the radar equipment and the drill broken down into small pieces up to the summit plateau. So this year, here's 3 of us doing a final day of radar. And then we set up our drill camp in 1 day. And this is what it looked like. It's quite minimal. Nothing is heated. There's just shelters over the drill. And of course, for sleeping. So this is sorry, there is sound on it. This is a quick look into the drill tent. I'll talk more about the drill in a minute. We were up there for almost 2 weeks, above 17,500 feet drilling. And I'll talk more about how we complete this too, but this incredible drill called an Eclipse drill. It was actually built in Whitehorse, and it allowed us to do the job. We drilled from the surface down to 327 meters this May. Yeah, this is the inner barrel of the drill coming out. It was about halfway down during the expedition. The sort of measuring and packing and stuff that we do in the field is very minimal. Once we retrieve the core and get it to the surface, it's basically about getting it babied in its packaging and ready to fly off the plateau, so it can get transported back here to Edmonton. Drilling is repetitive, but the nature of drilling changes as you get deeper and deeper. But this is kind of what it looks like day to day in the drill tent. And you can operate the drill with a very small team. We operated it with 2 to 3 people. We were down to only a few people by the end on our team. These last few shots, this is me going back to Prospector Call to service the weather station that I had installed last May. And shockingly, despite hurricane force winds that like to blow through there, everything has worked beautifully since May of 2021, minus the wind sensor. You can see there's nothing on the top of it right there. It was completely blown off. So this year we installed an acoustic wind sensor, has no moving parts and works acoustically. And it's been working well since we just put it on this May. And I'll talk to you a bit more about this weather station as well. And then here's the last shot of skiing down. It takes weeks to get up a mountain like this, and it took us 6 hours to ski from summit to base. Pretty fun. Okay, no, there we go. Okay, so I just thought that was a nice way to give a sense of what it actually feels like. So yeah, the little bits of the science here. So why do we install weather stations? Well, local meteorological data help put the more recent years of ice core data into context and ground truth some of that data as well. This station, along with one that was installed recently on Everest and Tupungato, make up the 3 highest weather stations in the world. The Logan weather station sits at 18,500 feet on Prospector's Call, the highest weather station in North America. And this has helped raise the roof of human observational networks as we lack meteorological data from high mountain environments for obvious reasons, which in many cases are located in parts of the atmosphere that are actually projected to warm fastest, but yet which are currently unmonitored. Now, Parks Canada, who has been instrumental as a partner in this work, has actually offered to accept an extension of my original research permit for the weather station for 5 years. And I think in part after seeing how valuable and access this data has been since the install in May of 2021. So I'm really excited that this, we didn't actually take it out this year. We're leaving it up for a few more years to gather data up there. And of course, this requires a commitment to service it when any components might fail over the next several years. But much like the install, I just hopefully can do this with one climbing partner and or Parks Canada. Now, I mentioned in May of 2021, last year, we completed a comprehensive ground penetrating radar or GPR survey on Logan Summit Plateau. So we towed 2 different frequency systems across the plateau last year, allowing us to image the internal stratigraphy or the layering of the ice from our skis all the way down to the bedrock below. And this allows us to locate an ideal drilling site where the ice is thick, of course, but more importantly, it's undisturbed in its layering, making it possible to date that really precious, valuable, deep ice that's the oldest. So we gathered many kilometers of data last year, which allowed us to narrow in on this ideal drilling location. And then this year, I mentioned in the playing of the video that we did one final day, sort of a fine, smaller GPS grid based on that data from last year to settle on that final ice coring site on the Summit Plateau. So once that was decided, within about 24 hours of us reaching the plateau, the helicopter began slinging up the drill in pieces. And we set it up in one long day, and then the drilling began. A quick note, I said I'd tell you a little bit more about this drill. I love this drill. So we drill in meter sections. It's a tipping tower style drill. So that hole where it says Eclipse Ice Drill on it, that entire, the thing on to the right of it, like the whole drill sonde itself, swings into a horizontal ice retrieving position where you can pull the inner barrel and the ice out. And then it swings vertically into the position you're looking at there, which is the drilling position. And again, so we drill a meter at a time. So as you can imagine, when you're at the surface, you can drill quite a bit of ice because the drill doesn't have much travel time. I think on day 1 here, we actually drilled almost 40 meters. It's usually more like 30. But you can drill a lot when you're not waiting around for the drill to go up and down the borehole. By the time we were below 300 meters, which is typical, you're only drilling a few meters a day. So the character of the drilling really changes despite it being, or at least appearing, somewhat monotonous. And in the field, my tactic here was to keep the drill running basically for as many hours as possible to decrease the time that we were spending at altitude. We started as a team of 7 and 3 people finished with me, which were all altitude related illness. And this was, I have to say, expected. I expected about half the team to be there at the end. So we kept the drill running for about 14 hours a day, drilling in 2 very small 1 to 2 person teams. And then the field processing for a setup like this is extremely minimal. You're looking at it on the left. We just basically weigh, measure, and then package the ice to get it ready to sling off the summit plateau, and everything else is done in the lab. Now, I also wanted to mention just quickly in one slide that while I took my team up high, Kira simultaneously led a team down low, which is really cool. She and her team also flew into Logan Base Camp. But when I went up, she took her team down the Seward Glacier toward the coast. And they dug snow pits all along the way at the sites you can see on this map, completing an elevational transect. So the snow pits are spaced at about 200-meter elevation drops from one another. And this allows us to see how the snow chemistry changes with elevation, and will help provide context for the interpretation of the more recent years of the Mount Logan ice core record. Now, I already sort of alluded to this, or more than alluded to it, but we think of these beautiful, pristine looking high mountain regions as sort of untouchable, and the last places to be touched by things like climate change, when in fact, due to a phenomenon called elevation dependent warming, they're actually experiencing higher rates of warming than lower elevations. And we know this to be true in particular of the St. Elias. So this is, that was also an important factor in deciding to install the weather station here. I get asked fairly often if it's too late. Is it too late, to change what the direction we're heading in terms of our climate? And my answer right now is no. It's not too late, but if you ask me again in 5 years, I may have a different answer. We have a very short amount of time to significantly decrease our greenhouse gas emissions to remain within what we know to be a 1.5 degrees C at this point ideal scenario. This is our current target. And I also often get asked whether changes that we make in our own daily lives can really have an impact. And they do, insofar as they show others, including policymakers, what's important to us. But the only way to achieve the emissions reductions that are required on a very short time scale are basically impacting policy. Now, I hope this ties together in your mind like it does for me with Logan, but the adventure of climbing Logan several times in the name of science and the allure of what we may learn from this new ice core have sparked an avalanche of interest, of curiosity and of collaboration and of wonder. And it's perhaps the last one, this wonder that I've seen across disciplines and backgrounds and ages, that I'm so proud of. We will carry this forward in hopefully impactful ways by leveraging this story to hopefully shift the needle on important upcoming climate policy measures. And this, I hope, will particularly be done through a film to be released by National Geographic in early 2024. The impact of this work has helped shine a bright spotlight on the Canadian Ice Core Lab, on our department and the faculty. And we don't have, the science papers aren't even out there yet. We just have the data in hand. It's not published yet. We've been on the cover of Globe and Mail, CBC, Quirks and Quarks. My colleague actually in kinesiology, sport and rec wrote this beautiful cover story for Canadian Geographic. And I wrote the current cover story that's just out this week in Yukon's magazine, Yukon North of Ordinary. It's just been incredible, truly, to watch the enormous interest in ice core science within Canada grow, particularly with, I think, adventure exciting projects like this one. And I won't read everyone out loud here, but as I mentioned right at the start, I am indebted to an enormous team of people and organizations that made this work possible. It's it's a team of superheroes. So thank you so much. I'm really excited to have a conversation, and you can follow the U of A website is there at the top, which is a great place to see what we have coming up. Thank you.
Well, thanks so much, Alison, for a fantastic presentation. Certainly lived up to the hype. And just for those keeping score at home, we got more than 170 participants in this month's Science Talks, which must be at or near a record. So if it's okay with you, Alison, I'm going to moderate questions from our audience, and hopefully, in our remaining time, we can get through most of those questions. Any questions that we're not able to answer during the presentation, we may try to follow up on afterwards. So the first Q&A that has appeared is from Gia Von Ten. And Gia writes, I got my BSc in Environmental Earth Sciences in U of A, and I applied for an after degree in computing science for fall 2023. I always loved glaciology because of Dr. Kavanaugh. In your area of research, what computing knowledge that would be highly what computing knowledge would be highly beneficial to your research? Could be fancy tech using AI, machine learning, or very low-level programming, such as optimizing hardware performance for higher resolution data collection. Alison, any thoughts on the intersection between computing science and glaciology?
That is a very timely question. I'm in conversation with a few other people across our faculty right now about this sort of interdisciplinary gap. This is amazing. Yes, so I think within glaciology and ice core science in particular, there's so much in terms of AI that can be done. There's a couple, just over the last year, really powerful papers that came out using self-organizing maps. And, I don't actually understand how this stuff works, but unbelievable work so far, and mostly in the Antarctic, using various AI techniques. So yes, I've been talking with a few others here at U of A about trying to find someone or some people to help fill this gap. And our group here doesn't yet have a computing science person that we work with. So I'm very excited to hear about your interest, and very timely.
Yeah, I think there could be real opportunities. And of course, as many are aware, the University of Alberta will be doing a cohort hire of CFAR funded chairs in the AI ML space, and it's entirely possible there may be some opportunities with these new appointments. Stephen asks if there's a profile of the GPR scans.
Oh, I should have had that on a hidden slide to show you. Yes. So the two of the folks who came in the field came particularly as radar experts. So I did the survey, but they in 2021, but Seth Campbell and Dominic Winsky at University of Maine have done all the processing. I have the radar grams and I have sort of the processed data, and I can tell you an overview of the report from them after last year's more comprehensive survey, which was that, so I towed around a 40 and 100 megahertz system, and they both were able to image down to bedrock, which according to Seth is unusual, and it immediately last year spoke to how beautiful the internal stratigraphy and layering, how undisturbed it was. Usually both frequencies won't make it down to the bottom. So I'm sorry, I don't have it prepped here right now on my screen to show you, but they're, as I'm not a radar scientist myself, and they're beautiful. The internal layering is very, it's spectacular. And the site that I ended up plunking down on was by no means the deepest ice, where the deepest ice is out in the center of the broad plateau. It looks like it's probably folded and disturbed at the bottom, meaning that we would sort of not be able to date the oldest ice at the bottom. It wouldn't be useful. So we picked a spot that was on a bit of a flat bench. The bedrock makes a bit of a flat bench. It's up tucked toward Prospector Call, off the main summit plateau. And yeah, there's just horizontal layering all the way down to the bottom.
So Alison, it sounds like the topology of the mountain really affects the sort of quality of the ice stratigraphy. Is that correct?
Yeah, I mean, it's this huge bowl. It is 20 kilometers long, but it's still, of course, flowing. So and the spot that we picked, in fact, it has not insignificant flow down from Prospector Call. So these are all things that we had to consider in site selection.
Okay, Andre asks a sort of a nuts and bolts question. Why wasn't it possible to fly directly to the plateau instead of climbing to it?
I sort of wish I could have flown. You can't go up to 17,500 feet from lower just physically. You would get some altitude sickness, pace, and
so it's about acclimatization.
It's just about acclimatizing. This is also why we use the that double carrying technique. It takes a long time to acclimatize and be able to work up high, and especially knowing we were going to stay up high for weeks, it was really important to go slowly. But yeah, I mean, even just flying into 10,000 feet from, some of the team being at sea level is a big jump. 0 to 10,000 is a big jump. But yeah, we have to acclimatize to safely work at those altitudes.
Okay. So Lawrence asks, do you have a time series from the ice core that shows temperature over the past 10,000 years?
Yeah, this is what I was tempted to show you. It's not on an age scale, right? So Kira and I just came back, I think 6 days ago or something, with the continuous data, which includes the continuous stable isotope data that we will make a temperature reconstruction from. So looking at it, and even though it's not on an age scale, you can see very clearly where the last glacial is. And there is a lot of ice below the last glacial. So we know that this is an enormous range, but it's, ice core scientists thought there's 10 to 30,000 year old ice sitting up there. And I still can't tell you exactly until we have a full age scale on it, but we have glacial ice for sure. It's 20 plus probably is what it looks like. So yeah, and the stable isotope, the temperature record is beautiful and very interesting. I'm sorry, I can't really show it yet.
Well, you don't want to scoop yourself. Okay, so Deb asks, she's curious if the weather station you installed also has any capability for greenhouse gas emission monitoring similar to the station on Mauna Loa.
That was only briefly talked about with the team actually in here in Edmonton at Hoskin Scientific that assembled this or built the station that we assembled. The winds and the temperatures are almost unrivaled. So as taking their advice that it wouldn't work at that location, we abandoned any attempt to monitor those sorts of things, which is unfortunate, but I think it wouldn't have lasted.
Right. Yeah. The environment is definitely challenging. Scott wants to know if, because of the elevation, that really limits requires multiple excursions for the helicopter, I guess, just because of the load it can carry. Is it going to have to make multiple excursions? And also, in passing, asks whether you can see Denali from Mount Logan.
I assume you meant when the equipment was being brought up to the summit plateau. Yes, so that's not a normal thing for helicopters to do at that kind of altitude. It's quite risky work and is usually just in a rescue scenario. But of course, in this case, it was planned. The payload at that elevation absolute maximum is 300 pounds, which is quite low. So this is with a very skilled pilot on oxygen, not landing, doing this all by sling load with 300-pound loads. So the drill itself is 900 pounds. So that was 3 loads itself. We disassembled it into 3 pieces and then rebuilt the drill up there to get it up there. And I don't know the total number of flights, but getting the drill and drill related equipment up and then all of that off, including what was almost 2,000 pounds of ice, was 25-ish flights.
A lot of trips.
Yeah. But what they did was basically they would take these 300-pound sling loads off the plateau and then down to kind of a staging area that's at lower elevation, but still on snow, and repackage there and take bigger loads out to the freezer unit that I'd staged at the landing strip. Yeah.
Right, and that staging area is enough lower that that the helicopter can carry a heavy load. Yeah. Okay.
Yeah. Yes. What was the second half of that question?
Oh, can you see Denali, Mount McKinley from the top of Mount Logan?
I haven't seen Denali, but Mount St. Elias, those panning shots in the video of the weather station, that's Mount St. Elias that you're looking at, that looks like it's right there, but it's like 40 or 50 kilometers away. And you can see the ocean and the Malaspina Glacier, which is the Piedmont Glacier in Alaska that spills out into the ocean and looks like this swirling mirage. It's incredible, but I have never seen Denali from the top. I don't know if you can.
Yeah, it might be too far away. Gia, who asked the earlier question about AI, wonders if there is any open database on ice cores and snowpack that they could play around with, in preparation for thinking about some of these intersections between AI and glaciology.
Yes. The ice core community is, I would say, working on having a more consolidated location to find all this, but the most consolidated location for ice core data at the moment is the NSIDC website. And I'd love if you follow up with an email and I can share. There's a couple other repositories that have really great data as well. The Polar Data Catalog, PDC. And we actually have our own internal one here at the Canadian Ice Core Lab that isn't available on the other ones, unfortunately. Yeah, but I would say I would point people in general toward the NSIDC. Yeah.
Super. So Kathy asks if you can comment on the progress of glacier thinning and climate warming on Mount Logan.
I can't really. There is no glacier thinning on Logan. There's no long-term, Parks is here, they might know more than me, but as far as I know, there's no long-term mass balance or any some such monitoring on Logan itself. So we don't have sort of long-term monitoring data. When I mentioned that we know that elevation dependent warming is a phenomenon that is happening strongly in the St. Elias, that is based on a paper from last year that used all available meteorological data. So there's sort of remotely sensed and metadata-based studies on this, but in terms of actual thinning of Logan's glaciers, I don't think we know. My comment about King Col icefall is sort of anecdotal, but resounding to anyone who has spent decades there. There's very clear change, not higher up on the mountain actually, but lower down from, I'd say 14,000 feet down. And one other thought I'm just having is that the Mountain Legacy Project, based out of UVic, that Mary Sanseverino and some other folks lead, has done some really wonderful repeat photography work. And Logan has some repeat photographs that were taken. I didn't mention this at all, but the 2021 radar survey that I completed. Zach Robinson from kinesiology came along on that and did a bunch of repeat photographs, including when we were on the summit. And those are being used by the Mountain Legacy Project, hopefully as a different way of getting at what you're talking about, like looking at actually like quantitative volume change through repeat photographs.
So you can actually,
Yeah.
I mean, I'm sure you can get coverage area, but can you get volume from repeat photographs as well?
Well, yeah, they have, and I guess this is another software thing, but yeah, that group at UVic has developed software to try to at least kind of interpolate.
Great. Here's a question from a grade 5 student. What do you look for when analyzing the ice cores to figure out what happened at different time periods of ice formation?
What don't we look at? Well, I'll tell you what we don't do in this lab are gases. We look at the liquid chemistry of ice in our lab. But looking at the gases is a whole other thing that I didn't even talk about, which will be analyzed on this core. It just wasn't the first priority. But
so there are bubbles in these cores then?
Oh yes, the bubble close off depth, like where fern becomes compacted enough that the bubbles are all separated from each other, and then we can utilize that to look at ancient atmosphere.
Wow. Is
somewhere around 80 or 90 meters in this core. Everything below that is ice, so we can measure for gases. So yeah, we will do that. But to very broadly answer your question, with what we were looking at in the liquid chemistry, I mentioned stable isotopes. So these are the isotopes of oxygen, and we use that to reconstruct temperature in the past. We look at all sorts of elements, some of which have to do with people and our impact on the environment, and some of which don't. But important ones being lead and black carbon and their isotopes. These can tell us sort of, how humans have impacted even these remote locations. And so I think we came back here with like 48 different elements and ions, each with their own story about the past.
Great. So here's a question that I don't understand because I think it involves some specific knowledge from David. Do you do any downhole logging, and if so, what?
We don't. This was mostly a time thing. Other groups, the Danes, do a lot of downhole logging. I spoke with some Canadian engineering groups about developing downhole logging capabilities for this project, and it basically just because of this payload issue and keeping things as light as possible, didn't go for it with Logan. But there's so much that we can gain from utilizing the borehole itself. It's already there. Sometimes even adding just a day or two of logging, if you've got some of the interesting equipment that's already out there that other countries have, is well worth it. We just couldn't do it with this project.
Right. And Andreas, a question that I can relate to: what is downhole logging exactly?
Well, once you drill something like this, you have a 82 millimeter diameter, 327 meter deep hole, and that you just walk away from. Yeah. That hole itself is very useful, right? You can image the sides of the hole. So there's all sorts of imaging and other technology that's been built that you just, it basically is on a line, on a tether, and you lower it slowly down the borehole once you're done with the borehole, when you're done drilling. And it can image and do other things with the walls and give you an enormous amount of information before you've even analyzed the core.
Are there any sort of temperature gradients in the borehole, or is it all just kind of the same temperature?
Oh no, there's a huge temperature gradient. So that's one of the other things that like deep drilling in Antarctica and other places, particularly where you don't have to climb, where you're not so constrained by weight and time. We always do this. So I said imaging and other other things we put on these tethers. One of them is always measuring the temperature profile of the borehole. At a certain depth, you sort of, there's a big change at the surface, and then you reach kind of a, the temperature. But yes, it's also very useful to get borehole temperature.
Okay, Samantha says, apologies if you mentioned this already, but where does the funding for projects like these come from?
I didn't really mention it. It's a good question. I'm originally, I'm originally American, and I'm here now permanently, but I'm used to NSF and NASA and a very different funding environment for kind of big, expensive science like this. And so I have learned in my time here, since I've been here since 2017 in Canada, funding big science and like this and polar projects it's difficult, and it's very different in Canada because NSERC and the CSA they're not NSF and NASA. So this project was funded almost entirely by National Geographic, which is kind of an unusual science funding partner. There's also smaller funding for this project from the North America's two alpine clubs, the Alpine Club of Canada and the American Alpine Club, that offer research grants. So like this was cobbled together with, I would say, fairly unique scientific funding, which has been, like a blessing and a curse, I don't know. But this has also been true of some of my projects in the Canadian High Arctic. I would say the same thing about. They're funded by private foundations in Canada. They're not funded by NSERC or large science foundations. So I think you have to be creative to do this kind of stuff here.
I've got two quick questions, and then I think we'll close off the question period. First from, and they're both repeat question askers. So you've got some very engaged audience members. So Gia asks whether the ice core work you're doing on Mount Logan has any relevance to planetary science elsewhere in the solar system, possibly Pluto, possibly, one of Jupiter's moons. I guess maybe Europa might be the best analogy, but in any case, can we draw any comparisons there?
No, but no, because Enceladus and the other obvious potential analogs are we hit the right temperature, but they're hypersaline environments. So there are places in Canada, not where this ice core came from, that I think are probably exceptional earthly analogs. And one of them is in the Canadian High Arctic, which is another ongoing project that I'm leading, where there is a subglacial body that does have those very cold, highly pressurized, quite hypersaline conditions hypothesized to exist on these other planetary bodies. But yes, Logan is not. There's no. It's a frozen bed. Also, there's no water down there.
Right. And last question from the grade 5 student who asked you the other question about what you look for, and kind of a just nuts and bolts question. How do you prevent your cores from melting before you get them back to the freezers in your lab?
A lot of stress. The absolute worst part of my job. We do all sorts. I mean, it took years to plan this and a lot of people, but it's different depending on where the core came from. In the case of Logan, I mentioned I had this -20 freezer unit, a CCAN, just a storage unit that was at -20 sitting in Kluane National Park at the landing strip, the area where we fly in and out of to base camp. So a helicopter, of course, the field is nice and cold, was sling loading the ice, basically to an intermediary spot, repackaging, and then taking it to that freezer unit that was sitting there, filling it up with ice with a person there dedicated to babysitting that. And so once that -20 unit was filled, in this case, we trucked it across the country. So it was the same way that frozen perishable food gets trucked around the country. So it got trucked from Kluane National Park all the way to the Ice Core Lab here in Edmonton.
It's a long drive.
But yeah. Oh my gosh, it almost beat me back. This guy drove it in like 3 days. Yeah, but it depends where the core is from. There's all sorts of ways to do it and keep it frozen. Yeah.
All right. Well, on that note, we'll conclude the question period, which was fantastic. So thanks again, Alison, for both your presentation and your engagement with the discussion afterwards. And I want to once again thank everyone in the audience for joining us for today's Science Talks. There will be a post-webinar email that will include other ways to connect, opportunities how you can support research and programs like Alison's here in the Faculty of Science, additional resources, and various ways to share your feedback. And I'll just remind you once again to watch for Science Contours, our magazine, which will be arriving probably in early January. And of course, we will be sure to reach out to everyone who joined us today to prime you for our next episode of Science Talks, which will be happening in early 2023. So until then, please take care of yourselves, stay in touch, and I wish you a wonderful, restful, and recharging winter break.